Let's redo the problem using the kinematics equations this time. So there's force acting on the charge due to the electric field. All right, and let's change R into X so that we can use the equations without changing any of the terminology. Based upon what's given, we can either use the second or the third formula. Time is not given, so the third formula is the only one that we can use. Electric field is constant, so which means that the force is going to be constant, which means that the acceleration is going to be constant. So the third formula is the only one that we can use. Initial speed is 0, so that drops out. Solve for V. We need to know what the acceleration is. We know that the acceleration is going to be caused by a force. A force happens because the electric field is acting on a charge. So the electric field is going to induce a force on a charge. And force is what causes acceleration. So we do a back substitution. The only thing we're missing right now is the mass of the electron, which is not given. So we have to look that up. And then plug the numbers in. Then we will get the same answer as we did previously for the speed of the electron. So the kinematics will work just the same as the conservation of energy.
Forward. Okay, let's revisit the lightning problem. High ground versus low ground. Which one is more likely to be struck by lightning? All right, high ground is more likely to be struck by lightning. And if that logic is so correct, why is it that it does not strike the tallest building 100% of the time? Okay, so why do we even think that it's supposed to strike high ground more often than the low ground? All right, let's get back to the logic on that. All right, good. Reverse subsequence number. High ground versus the low ground. All right, mathematically, here's the reason why. All right, so boom, boom, boom. So initial separation of the charges because of friction among isotopes. I'll place the high ground here, and then we got the low ground here. And then the for reasons which are not quite well understood, the negative charges will sink to the bottom, the positive charges will rise up to the top. Negative charges at the bottom of the cloud, so these charges at the bottom of the clouds. Despite the fact that the Earth's initial negative charge will become positive charge because of polarization. So the Earth becomes positive charge. Separators start coming from the clouds, the streamers will start going up, and then they will make contact, and then you get your lightning hammer. All right, so that's what we discussed so far. All right, so the lightning is whatever. Okay. So the question is, high ground. Why is it that the high ground is more likely to be struck by lightning? Okay, so I'm gonna make this distance between the high ground and the clouds about a one single football field in length, and then the low ground in the clouds. I'll make this about 10 football fields in length. And instead of using the electrical breakdown of the electric field that's responsible for the electrical breakdown of the air molecules, that's to me is a little too much. What I'm going to use is the measured electric field inside the lightning bolt. All right, so that's what we will use. All right, so here's what we know. Strength of the electric field, measured strength is usually S, according to one of the books. So I wasn't able to verify that. I couldn't find that information anywhere else. Only in one of the physics books. I'm not sure where they got it from. Somebody must have measured it. Okay, so R1 is going to be a single football field in length. This is about 100 yards, 100 meters, give or take. R2 is going to be 10 times that. 10 times that. All right, so I'm going to make this 1,000. Okay. So I'm interested in the voltage or potential difference between these 2 points. All right, that's what we're going to look at. And then I'm going to be interested in the voltage difference between these 2 regions. All right, so that's what we're going to focus on. Voltage or voltage difference, they mean the same thing. Depends on the strength of the electric field and the separation distance. All right, I'm not sure why this working. That's working. All right, so for this region, I'm going to call this V1. All right, so that's the region that we're looking at. It's going to be the strength of the electric field, constant separation distance. All right, so this is going to give us 1, 2, 3, 4, 5, 10,000. All right, so this gives us 100,000 volts. Am I missing something?
Yeah, the R1 should be 100, not 10.
Okay. Oh, yeah, okay. Man. All right, so that's the advantage of being a physicist, guys. You don't need to be good with numbers. It's only engineers can't get away with that bullshit. If a building comes down because you don't get numbers, if that's the case, blame the physicist. All right, it was done. All right, so we got a million, right? All right, so we got a million volts. And V2 is going to be straightforward. This one is going to be 1,000. And so this is going to be 10 million volts. Oh my God, I know how to conclude this right now. I'm excited. All right, so the voltage difference between the high ground and the clouds is going to be 1 million. The voltage difference between the low ground and the clouds will be 10 million. And hence the reason why I will say with 100% confidence that more than likely it's going to strike the high ground. That's it. Okay. Except what the hell did I just say? How did I arrive at that conclusion? How did I know that at 1 million volts it's more likely that it's going to strike the high ground than at 10 million volts it's going to strike the low ground? How did I arrive at that conclusion? Okay, guys, looking at these numbers, you can conclude that more than likely this lightning is going to strike high ground. How do we arrive at that conclusion? Any ideas? All right, enough suspense. You need to focus on the meaning of voltage. Voltage is the amount of energy stored per charge, right? You need to remember that this is joules per coulomb, which means that this region is going to have enough energy per charge to jump this gap. All right, so the clouds, these charges will require enough energy to jump this gap sooner than jump this gap later. All right, so the energy is going to build up to 1 million volts before building up to 10 million. That's what it means. So these charges will require enough energy to jump a smaller gap sooner. That's what it means. Is that making sense? That's what it means. Okay, so by that logic, if that logic is so correct, 100% of the time, oh my God, lightning should strike high ground. 100% of the time, 100%. All right, 100% of the time, the lightning should strike high ground. So here's a question for you. Forget the details of all the videos that we've seen, just based on the physics that we're discussing. Why is it that it's going to strike high ground about 70% of the time and 30% of the time it's probably going to miss high ground? Why is it that this is not 100% of the time correct? Any ideas?
Because after the lightning strikes, it neutralizes the positive charge.
Okay, so Ian, I'm going to give you 2 points for that one. My question is, why is it that it's not striking the high ground or the tallest structures 100% of the time? Okay, guys, the reason the high ground or the tallest structures are not the ones who get hit by lightning is because charge distribution is not uniform. It's not like a capacitor. You get it? In the case of a capacitor, you have a nice uniform distribution on a flat surface. Here, you may have a larger concentration of charges, negative charges, or sometimes you have a higher concentration of negative charges here. Got it? So it just depends on the concentration of the charges. So the charges are not necessarily uniformly distributed under the clouds, and they're not uniformly distributed on the ground either. It's random. Hence the reason why lightning is a random phenomenon. All right, it's very unpredictable. You don't know where the high concentration of the charges are. These are not smooth surfaces. All right, the charges are uniform. They're not uniformly distributed. All right, most of the time, this logic works out because, because of the proximity of these regions, you end up getting more negative charges here. The reason is because most of the ground becomes positive charge very strongly. And then, boom, charges will require enough energy to jump the gap at an earlier point. So, going back to it, charges will require 1 million joules of energy per coulomb of charge sooner than requiring 10 million joules of energy per charge in order to jump a larger gap. That's the short answer. And that answer is not 100% valid 100% of the time because, unlike capacitors, the charge distributions under the clouds or on the ground are not uniform. All right, so physics still holds. Physics doesn't say 100% of the time is correct. Physics says more than likely this is a good explanation. All right, enough guessing regarding this. All right, moving forward. All right, so now just before the lightning strikes, what are the telltale?
I wanted to show you that electricity can actually be useful. So when my young friend here told me that she wanted her hair teased, I thought maybe I would do it on this Van de Graaff machine. This won't hurt a bit. There we go. Now watch what happens when I turn it on. You see that?
All right, so notice that the hair is rising up. Just before the lightning strikes, this is one of the things that you may witness. What does it mean if you see somebody's hair just rising up in this fashion? What causes it? So what happens to the ground? It becomes positive, right? It becomes positive charge. What happens to the human body? Once again, the top of your body is going to become positive charge. What happens to the light charges? The hair strands.
Oh.
Yeah, they will repel.
Electricity can be absolutely hair-raising. She wanted to know how much this would cost, but I told her that by the time I was finished, there'd be no charge.
Oh, that guy really enjoyed it. Must have a really deep understanding of physics. I take it that he's a physics major. There you go. This is how. All right, so pick out the best answer and tell me why that's the best answer. All right, for the person who's providing the explanation, I'm going to give you 5 points, and those of you guys who come up with the right answer, I'm going to give you. So why is A the best answer?
Because it's a direct proportion.
All right, so the potential difference is directly proportional to the separation distance for a given electric field, right? So you can give yourself 5 points. Those of you guys who picked A, just 2 points for the other one.
One of the most surprising discoveries is that lightning is blind as it streaks through the Earth. It is only in about the last 100 feet that it senses the Earth's electromagnetic field and selects a place to strike. When it does come down, you can see in this picture here that it's coming in little 50-yard steps, 50-meter-long steps called step leaders. It keeps coming down toward the ground, and this part of the channel, this is the one that made it to the ground. As it comes closer to the ground, and it gets down to this last little part here, this is a really important part. This last 30 to 50 yards, it looks for something to hit just in this little area. As the step leader streaks towards the Earth, anything sticking up, buildings, trees, even people, send up positive streamers in response. When they connect, lightning is born. Negative electrons are discharged to Earth, and a positive charge travels back up the cloud at 60,000 miles a second. Here, 2 streamers leave the tree, but only one successfully connects with the step leader. The telephone pole has also launched a streamer, a failed lightning bolt. Packing up to 100 million volts of electricity, lightning has the power to explode walls of concrete and destroy electrical systems. Each bolt is 5 times hotter than the surface of the sun. Exposure to its power for a fraction of a second can be lethal.